So this is figure 34-3, right? And what we're doing is just calculating what voltages we should measure to see if Rich has the circuit hooked up right, right? And I redid it and spread it out so we could make our measurements a lot easier than me shorting everything out. So why'd y'all come up with VC? And up here we have plus 10 volts. So VCC is equal to plus 10. I just didn't put it on the diagram. What's that? VRC, yeah. Whatever you calculated for VRC. So VCC, this is going to be equal to VCC minus VRC in this formula. But to do that, you got to calculate IC, right? And IC is going to be equal to what? 1.05 divided by 2.2K. So what do we get for IC? And then VRC would be equal to 6.8K, right, times 477 micro. .2, that's not good. 3.2 volts. Yeah, so it's going to be VC is going to be equal to 10 minus 3.2. Huh? 6.8. And then voltage collector to emitter is going to be voltage on the collector, 6.8, minus voltage on the emitter, 1.05. What we got? Yeah, voltage on your, and that's in, it tells you the formula. It says take whatever VC is equal to, which is 6.8, minus whatever VE is equal to, which is 1.05, and this will give us our voltage collector to emitter. So here's VB. .73. That's pretty good, ain't it? Here's VC. I'm sorry. Here's VE. .0. Pretty good, right? Here's VC. 7.15. Is that what we calculated? 7 something. Yeah, well, that's not bad. So it looks like the circuit might be built right. So what we're going to do, and what voltage gain should we expect right now, the way it's wired up? So R out will equal to 1 over 6.8K plus 1 over 10K. So this is not the 10-to-1 rule, so we know it's going to be less than 6.8K, but we'll have to calculate this. Can y'all see that? Everybody okay? Yeah, we just take the reciprocal of our answer, right? I don't think I have my calculator out. So this would be 6.8 times 10 to the third, right? Reciprocal plus 10 times 10 to the third reciprocal equals reciprocal. About 4K, 4 point. Yeah, so so R out equals what, 4,000, what, ohms? 4,000, what did y'all come up with? 47? So AV would be equal to 4,047 over 2.2K right now, which is going to give us a gain. This is not a real good amplifier, guys, but we'll look at something in a minute that's going to drastically change this. What's that? So we're going to bring an AC signal in, and like I said, you know, we're not going to do audio because audio is real hard to do that, and I'll show y'all some audio here in a minute. So we calculated everything out, so that means if I come over here and put a certain voltage in, so let me fire up my function generator, and by the way, I changed all my capacitors to, where's my potentiometer at? Oh, here it is. I'm going to have a, what did I do with my long ground? Here's one. Hey. What do you mean? Well, you don't know the voltage drop across 6.8K. We know the voltage drop across RE, because RE. So we know the voltage drop across RE, excuse me. We know the voltage drop across RE, and we know the size of RE. So since I know the voltage drop across RE and I know the size of RE, then I can calculate IC is approximately equal to. Y'all understand it's not equal to. So what's the difference between the current flowing through this guy and the current flowing through that guy? So IC is equal to what? I'm sorry, IE is equal to IC plus IB. So technically IC would be equal to IE minus IB. But the problem is IB is so small, right? You understand that we assume that IC is equal to IE because there's not enough to even affect our math. Just simply with the tolerances of the devices, right? You understand? So I wouldn't say that IC is equal. I would say IC is what? Approximately equal to this voltage, 1.05 divided by 2.2K. Because we know that voltage. We don't know the voltage drop across RC. We use IC to calculate VRC, right? You understand, Austin? So which one do we use? We don't use the 6.8K to calculate IC. We use the what? The 2.2. Because once I find this, what does this measure the base? This is going to measure 1.7. This calculate 1.75 volts. Then I know that guy right there is going to be 1.05. And now I know the voltage across it, and I know the size of it, so I can calculate IE. But what are we saying? We're saying IE and IC are basic. We're using the same thing. So that answer your question? You okay? So why can't you use the 6.8K? Because you don't know the voltage drop across it, right? Once we find IC, we can calculate that. But we do know the voltage drop across RE because RE is going to be 1/7. It's going to be minus 0.7 from the base. It's 0.7 exact. If I said a silicon diode always drops 0.7 volts, what would that answer be? That would be false. It's approximately, right? You understand? Yeah. Yeah, nothing is exact. But they're exact enough. You see how close that was, even though we used the 7/10, how close it was. It wasn't exact, but it was what? It was close enough, so I know I had the circuit connected right. And later on in this lab, guys, we're going to deliberately put problems into this circuit. And you're going to be able, by looking at these, knowing what these bias voltages are supposed to be, you'll be able to tell exactly what's wrong with this circuit. You'll be able, this guy is one of the easiest circuits to troubleshoot if you got a problem right here. So we're not getting a good voltage gain out of this. We're getting a little bit. We could rearrange that, right? We can make RC bigger and RE smaller, but right now we're getting a very small voltage gain until we do something here before long, and it's going to be amazing what's going to happen. Okay, so we measured our voltage, and what I'm going to do is I've changed my circuit over. We don't have this capacitor hooked up yet. What do we call these capacitors right here? If we call it C1 and C2, what are they technically known as? Coupling capacitors. They're in there to couple the AC into the amplifier and couple the AC out of the amplifier, right? You understand? And their main function is to block AC and pass DC, block DC and pass AC. I'm using 100 microfarads here, all three. So I did modify the circuit a little bit to make it have a better frequency response. And this one, when I hook it up, this is going to be 100 microfarads. Okay, so we're going to throw a signal into it. This has nothing to do with what we're going to measure. And we're not going to do AV yet. But down here in chart 34-4, we can't do RE prime. That's why I got to explain to you. So there's nothing we can really do yet down there. Okay. So let's see if this thing gives us our gain. So let me turn on my oscilloscope. And I'm going to put channel 1 across the input. Where's my big wire with this? Here it is. just do? I'm gonna use another wire. What's that? And I'll put channel 2 across the output, and I'll bring this up in a second, guys, when I get it. Oops. So my channel 1 is on 2 volts per division. And then my channel 2, huh, it don't look like we're getting a gain of doing. Oh yeah, it's reading it wrong. There we go. So I have 1 volt per division on channel 1, and I have 1 volt per division on channel 2. So it looks like we're getting more. So this would be 2 volts. This would be 1, 2, 3, 4, 5 volts. A gain of 5. What do we calculate? Wonder why our gain is off so much. So I've got a 6.8K. That's R. That's RC. And then I've got a 2.2K. Oh, here we go. And then I got a 10K is R2. Are those right? Nope, wrong side, Rich. 2.2K. So 6.8K. What's the color code for a 6.8K? Hmm. Great, maybe. Yeah, that's the same game. I don't look great to me. They gave us a little bigger, they gave us a little bigger game, right? This is giving us a gain of 6. What color codes do those look like to you? Yeah, the eight is, I guess it's gray. I couldn't see that one. It was in the 6.8K drawer. I'll give y'all a handout. So if I was to come up here, and this is, we'll talk about this, and then we'll finish this up next class, because I know it's almost time for a class to be over. Don't you get over 12:30? So what's going to happen is when we come over here and do this, we know that 1,000 hertz, we calculated a while ago, this guy here has approximately 3 ohms worth of resistance to it. So here comes my AC signal coming in. We know some of it goes this way, right? Some of it goes this way. And then it comes to this guy. Now you got an option of going through 2.2K or 3 ohms. Where's 99% of the current going to flow? Through the 3 ohm or for the 2.2K? So if I was to come up here and put a 10-volt supply up here, and I came over here and I put a 2.2K ohm resistor right over here. Let's say this is 10 volts. And then over here I put a 3 ohm resistor over here. This is 2.2K. This is 3 ohms. And let's call this R1 and R2. Then IR1 would be equal to 10 volts divided by 2.2K, and IR2 would be equal to 10 volts divided by 3 ohms. So which way would most of the current go through? Would it go through the 3 ohms, or would it go through the 2.2K? Huh? Okay, so let's calculate the current. I just made up something. I said, okay, I've got a series circuit, got a parallel circuit over here, and this concerns me, guys. And let's say I've got 10 volts over here, plus 10 volts, and over here I got a 2.2K, and over here I got a 3 ohm. So over here, if I was to calculate R for this first one, it's going to be 10 volts over 2.2, 2,200 ohms. Over here, this is going to be 10 volts divided by 3 ohms. Which one's going to conduct the most current? The 3 ohms, right? It's a parallel circuit. So that means here comes this signal. 99% of the current is going to flow this way. It's going to bypass R2 or RE. It's going to bypass RE. Well, heck, we used RE to calculate our gain, but the AC signal is not going through RE anymore. It's bypassing RE, right? You understand that? So what would be the gain? A while ago, if we said AV would be equal to R out over RE. Well, the problem is what's our signal doing now? Bypassing RE. So basically, if it bypasses RD, if we use 0 ohms right there, we say the amplifier has a gain, but it don't. So what happens is this guy right here, this right here has a resistance. It's called the dynamic resistance, and it's referred to as RE prime. And there's a formula in there for calculating RE prime. Can y'all give it to me? So what did we calculate for IE? So what would RE prime be equal to? $52. And this would be ohms. Everybody get that? Everybody get that? Everybody? Or something called RE prime, I'm sorry. Now what I'll do Thursday. So RE prime is the dynamic resistance of a PN junction. We know that the resistance varies, right? Y'all understand that? I'll give you a formula sheet. I'll give you the way it's solved for. I'll give you all that out Thursday, and it's a very complicated formula. But so this is an approximation. So if you look at that other formula, it says AI is equal to I the low, I out, which is what do we calculate for I out? $4,047 ohms. Over 52 over RE prime 52.4. So what would the gain be? $77. So let's watch this. I'm gonna have to lower my input down to almost nothing. probably still going to saturate. I'll probably have to do a little better. And watch what happens when I bypass RE. So the blue is my output. It's not triggering. So what I'm going to do is I'm going to bypass RE. What's RE? That's a 2.2K, right? Of course, what we're doing is we're saturating our transistor. I'll have to try to adjust my input down as low as I possibly can to try to keep it going into saturation. We'll change our trigger over to channel 2. So here's my input. We can't keep the noise from getting out of it, even though you can tell it's a nice smooth signal, but my scope is picking up noise. What we're doing is we're measuring the output, which is across the collector, right? And we're measuring the input voltage now. So this is without it bypassed. So this is my output. This is my blue, and you can see it's way down here. And then I'm going to bypass RE, and you see the gain of the amplifier jumps up. See that? So what I'm doing is I'm putting in I'm putting in 10, 20, 30 millivolts, and I'm getting 1, 2, 1, 2, 3, 3.5 volts out, just by bypassing that resistor. So what would that be? 3.5 divided by what are we putting in? So we're putting this in. That's 110 millivolts per division, 30 millivolts, and we're getting what out? 1, 2, 3.5 volts out, because I got it at 0.5 volts per division. So that's 3.5 divided by 30 milli, though, not 30 milli. So what's our gain? Well, yeah, that's a lot. So we got to go back and figure it out. So let's figure out what's going on. But this is with it. This is with that resistor bypassed. This is with it. This is with it not bypassed. This is with its bypassed. So I need to come out and double check my resistors, because we calculated a gain of around 2, and we're actually getting a gain of almost 6. So I'll have to do that and figure out what's going on. But you can see what happens when I bypass. Now, guys, you got to realize you don't get something for nothing, right? You understand that? And we'll talk about what we just sacrificed to get this big gain. We'll talk about that Thursday. And I'll let y'all. I wanted to show y'all some audio too. Just then. We'll come back and review. We'll come back and look at it again. Well, you did okay on the voltages, right? You was okay on those, the Lab 33, the one we did before this one. Yeah. In calculating the voltages, we're okay there, because that's just right off the worksheet, right? We did that. So where we having problems with is these gains and stuff, right? Yeah, but what I want you to do, guys, is I don't want you to memorize the formulas because every formula, almost every formula, you were supposed to learn where in this thing. Well, let's think about what you need to know and let me know Thursday, and we'll come back and we'll talk about that. Okay. Like I said, we're gonna record this, and if y'all see Brian, I think Brian is the only one that ended up the absent. If y'all have many classes, let him know he needs to do. So I lost you today, huh? Yeah. Don't that look impressive though? You're okay on the voltages though, right? Calculating these voltages. VE, and then we have to calculate IC to get that voltage up there, right? Yeah, 1 point this divided by this, and then we use that to calculate the voltage drop up there, right? VE gives you, we called it IC, but it's not exactly. Yeah. In fact, there it is up there. Yeah. 1.0, 477 micrograms. And we use that to calculate VRC. So VRC would be equal to its size, right, times the current that we calculated down here. Because this is basically a series circuit. We do have a little bit of emitter current going there. So we calculate this guy here first. We call this IC. Then we use that to calculate this, right? You understand? That makes sense? Yeah. Then we subtract it to get what we would measure right here, according to Kirchhoff's law. So Kirchhoff's law, this guy here is dropping 3.2. So that means between here and common, we must have 6.8 volts left over, right? I understand. Yeah. Oh, you mean the worksheet? Yeah, because all this is DC. You know, you know. In fact, when I used to teach DC, I used to teach this, and so they could actually see how this is going to apply later on in an active circuit, where they actually says, okay, I know why I'm solving for these now because when I get to transistors, everything that I'm learning in DC is what you learn. I mean, everything you're learning in DC, you'll use that in solid state. Well, it does. If you look at my corrections, uh, yeah, you have to do all your calculations, and that's why we went ahead and did it first. And then, well, basically to see if it's working, these are the main ones, but we got to calculate all these to get these, right? You understand? So when I measure an amplifier, I measure VB, then I measure VE, I measure VC, and then I can either calculate voltage collector to emitter, or I can move my meter right here. Normally we don't measure it because these leads are so close together. So normally we just do that formula. We just say what? Collector voltage minus the emitter voltage. The guy actually tells you the formula. So I take whatever's on the collector. What did we get on the collector? I don't know where it's at. 6.8 volt. Subtract with what's on the emitter. What's on the emitter? 1.05, and that gives you the voltage collector to emitter. And so the actual designator gives you the formula. This minus this. No, then we come back. This is something new. This is a new formula down here. Right now, that's what we need to understand. How we can come up with all this stuff over here. And all I said, okay, I'm going to see if my amplifier is built right. And what we're going to do later on is we're going to open up these resistors. We're going to say, okay, what's going to happen if I open up R1? What's going to happen if I open up R2? What's going to happen if I open this? What's going to happen if the transistor goes bad? And you'll find out that these measurements right here will tell you what's wrong with the amplifier.
Okay.
You can tell what's wrong within 2 parts. Yeah, if we don't, that's forming for R out, right? It's this and whatever we're loaded with. And then we'll explain why. Right now we're loading this with a resistor. So an amplifier would be no good if you didn't use it for something, right? You understand? So here we're going to use it to create heat. Normally what we do is we'd use this and we would go into another amplifier. So then the gain gets more complicated because Rn of the next amplifier would be in parallel with that. But we'll talk about that, but we're not going to get in detail, just so y'all kind of get a feel of what's going on. So most of the time when you get out and troubleshoot, these voltages are given to you, hopefully. And it would tell you what you're supposed to measure. But if you don't know what you're supposed to measure, then if you don't know what you're supposed to measure, then if it measures wrong, you don't know if it's right or wrong. Right. So even if they give you this voltage in your schematic, you still need to say, okay, what would it measure if this right here would open? Well, that's pretty obvious because that's where it gets its voltage. So if this guy opens, this guy here is going to be pretty close to 0, right? Understand? And of course, that's going to cut the transistor off. If this guy drops, this guy is setting to 1.5 volts. So this voltage is going to go way up now, and if it goes way up, the transistor is going to saturate. If this capacitor opens, then your gain of your amplifier is going to be a lot less than what you think it's going to be. I mean, way down. So we came over here, we had a gain of 52. When we calculated this, we had a gain of 2. So what's going to happen if this capacitor right here opens? That means instead of getting a big gain, we're going to get a what? A little bitty gain. And so right off the bat, these guys, if this guy right here shorts, then this voltage right here is going to go to almost 0 again. So if this goes to 0, you got 2 problems. Either this capacitor shorted or that resistor right there is open. So normally bad measurements don't tell you a lot of times it will tell you which it is, but normally it gets you within 2 where you can figure out. And this guy would be easy because you can pop one lead and measure it. And this guy, if you measure across this guy, with your meter, this guy right here is pretty close to infinity. And so if you put your thing across there and measure pretty close to 0, this guy right here is shorted. So, and that's what we're shooting for. The math is nice and pretty, but what's so neat is that you can figure out what you're supposed to measure before you even hook up a meter. So, in this guy right here, we added this guy right here. This guy's weird, and we'll have to explain what's going on there. But what happens is over 90% of your current goes which way now? Because it's AC, so we're putting AC in. It goes this way. And it bypasses this guy. So this guy's called a bypass capacitor. But what did it do? It changed the gain from what? This to this, which is pretty neat. I'm not it changed the gain from I didn't write this down. To this over this. What was that? Yeah. No, the one we're going to give you Thursday is going to show you how they come up with RE prime, how they came up to calculate RE prime. How did they come up with this thing right here? How did they come up with that constant right there? That 25 million. Yeah. We're still using V over I, but this is the constant. And so this is the constant that we can go ahead and use. So what I'm going to show you Thursday is I'm going to give you out something that we'll never use. But it shows you how the people in physics calculated that guy right there. And I'll say, okay, you can use this big long calculus formula, or you can use 25 millivolts, whichever one you want to use. This is close enough. No AV deals with what's going on over here, right? So we put a voltage over here, but your voltage gain is what difference you have from here to over here. So if I know what I'm putting in, I can measure what I'm getting out, and I can get that would give me my voltage gain. But the problem is, if I measure it, it means nothing unless I know what to expect, right? You understand what we're saying? So all I know is this guy's going to give me more voltage out than I put in from the power supply. These guys don't create voltage; they manage this guy right here. Okay. So I know if this thing's designed right, I'm going to get more voltage here than I'm putting in right there. But if I don't know what to anticipate, then, if I put 1 volt in and get 2 volts out, I know I'm getting a gain, but is that the right gain, right? Does that make sense? So what we do is when this guy's not bypassed, we see it's pretty easy. So if I put 1 volt right here, that's going to create current, and the current goes up through here and creates a voltage in here that's proportional to these 2 resistors. So we say, okay, I can take this resistor and divide it by that resistor, and that gives me the voltage gain because it's the same current flowing through both of them, right? You understand? Yes or no? Well, if I came over here and let's just say 1 amp. So if I came over here and I put 100 milliamps. If I came over here and I put 100 milliamps over there, we would see that this guy right here would drop a voltage. But that same 100 milliamps is flowing through this. This is going to drop more voltage. It's going to drop exactly, 3 times more. Exactly 3 times more. Right? You understand? Because it's what? It's about 3 times bigger. Right? You understand that? So if this guy dropped 3 times more than this one, that means its output over here is going to be exactly 3 times less. Exactly 3 times less, so it drops down here. Okay, so when this current goes up, this guy goes up. This current goes up, this guy drops more, which causes the output to drop. But it's going to be exactly the same ratio, right? You understand what I'm saying? So if this goes up by 1/3, this right here is going to raise by 1/3, right? If this drops down, if this goes up by 1/3, this is going to raise by 1/3. So what that means, I can calculate the voltage gain by just dividing this by this. But what we did is we just threw a wrench in the fire when I did what? When I bypassed this resistor. So now the amount of current that I'm getting from my input is not determined by this guy anymore. It's determined by how much resistance we have right here. And we call that RE prime. And we have to just we have to use this because the math to actually calculate it, you would have to know the actual temperature that's around here, and not in Fahrenheit. You'd have to know it in Rankine, and you'd have to do all this math, and it would always come up to be pretty close to what? To this. So this is an approximation, but 25 millivolts or whatever IE we calculate, and it's pretty accurate, but it's not totally accurate. So what our formula changes to is R out over RE prime. Our original formula was R out over RE. Well, what we just did when we put that capacitor in there is we bypassed what? We bypassed RE. So I need to know the actual resistance of this junction right here, the AC resistance of this junction right here. And that's where this 25 millivolts, that's where the 25 millivolts over IE comes through. And that's the dynamic resistance of a PN junction. So that changes our formula from that one to this one. Yeah. So we went from a gain of 2, and unfortunately I didn't write it down. I need to go eat lunch. Into a gain of 4,047 divided by 52.4. So we went from a gain of 1.8 up to a gain of, what did I get? 77, yeah. I need to keep this on.